Ton 618, the King of the Abyss. Our universe is a place of breathtaking beauty and incomprehensible violence. It is a cosmic stage where forces beyond our imagination play out over scales we can barely grasp. We see the gentle light of a trillion stars, but hidden in the dark between the galaxies lie the true monsters of the cosmos. They are the titans of gravity, the points of no return. They are black holes. We know of stellar mass black holes, the ghostly remnants of dead suns, a few times the mass of our own star. For decades, we have also been in awe of the supermassive black holes that lurk at the hearts of galaxies, including our own Milky Way. Our galactic anchor, Sagittarius A, weighs in at a staggering 4 million times the mass of our Sun. Then, in 2019, humanity saw for the first time the shadow of a true giant, the black hole in the galaxy M87, a beast of 6.5 billion solar masses. For a time, it seemed we had found the peak of cosmic gluttony. We were wrong. Far out in the cosmic ocean, in the dim constellation of Canes Venatici, lies an object so massive, so luminous, so extreme, it defies easy categorization. It is an object that makes a 6.5 billion solar mass black hole look like a lightweight. This is the story of the undisputed king, the heavyweight champion of the cosmos. It is a behemoth so large that it challenges our understanding of how the universe even works. This is the story of Ton 618, the largest black hole ever confidently measured. The star that wasn't. Our story begins not with a hunt for monsters, but with a simple mapping project. In 1957, at the Tonantzintla Observatory in Mexico, astronomers were undertaking a photographic survey of the sky. They were searching for faint blue stars, a specific type of hot young star often found in the halo of our Milky Way. Among thousands of candidates, one was cataloged as object number 618. Tonantzintla 618, or Ton 618 for short. For over a decade, that's all it was, a faint, blue, seemingly unremarkable star, presumed to be a neighbor in our own galactic backyard. But this star held a secret of cosmic proportions. The truth was revealed in the 1970s with a new tool, spectroscopy. By breaking down the light from celestial objects into a rainbow of colors, astronomers can read their chemical fingerprint and, more importantly, their motion relative to us. The light from Ton 618 was strange. It showed spectral lines that were enormously shifted towards the red end of the spectrum. This wasn't the signature of a nearby star. This was a colossal redshift. A redshift of this magnitude could mean only one thing. The object was moving away from us at a tremendous velocity, carried by the expansion of the universe itself. And that meant it wasn't a star in our galaxy at all. It was located an almost unbelievable distance away, over 10 billion light-years from Earth. The light we see from Ton 618 today began its journey when the universe was less than a third of its current age. But this revelation presented an even bigger puzzle. If it was so incredibly far away, how could we possibly see it? For an object to be visible from 10 billion light-years, it would have to be shining with an unimaginable power. The calculations were stunning. Ton 618 was radiating with the light of 140 trillion suns. It wasn't just bright. It was one of the most luminous objects in the entire known universe. No single star, or even a cluster of stars, could produce this much energy. There was only one known phenomenon in the cosmos that could, a quasar. Ton 618 was not a star. It was the blazing heart of a distant, ancient galaxy, powered by an engine of unimaginable scale. Anatomy of a Leviathan. To understand Ton 618, you must understand the nature of a quasar. The brilliant light we see isn't coming from the black hole itself, for from within a black hole's grasp, nothing, not even light, can escape. What we are witnessing is its final meal. This light source is the accretion disk, a cosmic whirlpool of gas, dust, and the shattered remains of stars, all spiraling towards their doom. As this material is drawn in by the black hole's immense gravity, it gets compressed and accelerated to near the speed of light. The incredible friction and magnetic forces at play heat this matter to millions of degrees. It glows with a ferocity that can outshine its entire host galaxy by 1,000 times over. A quasar is the death scream of matter, and Tan 618's scream is the loudest of all. And at the heart of this inferno sits the engine, the monster that drives the entire spectacle. An ultramassive black hole. But how do we weigh an object we can't see, from a distance of 10 billion light-years? The answer, once again, was hidden in its light. The light from the gas clouds swirling in the accretion disk gives us vital clues. The faster the clouds orbit the central object, the wider their emission lines become in the spectrum due to the Doppler effect. Some of the gas is moving towards us, blue shifting its light, while gas on the other side moves away, red shifting its light. This smears the spectral lines, making them broader. By precisely measuring the width of these lines, astronomers could calculate the orbital speed of the gas. And according to the fundamental laws of gravity, by knowing how fast something is orbiting, you can accurately calculate the mass of the object it's orbiting around. When the final calculations for Tan 618 were completed, the result was world-changing. The engine at its heart, the central black hole, weighed in at 66 billion times the mass of our Sun. Let's try to comprehend this number. It is a mass so great that it is difficult to find a suitable comparison. If you were to take every single star in the Milky Way galaxy, all several hundred billion of them, and extract their mass, Tan 618 would be more massive than about 10% of our entire galaxy's stellar mass combined, all concentrated into a single object. Its physical scale is just as horrifying. A black hole's point of no return is its event horizon. For a black hole the mass of our Sun, this would be a sphere just 6 kilometers across. For Sagittarius A, our galaxy's central black hole, it's a region roughly the size of Mercury's orbit. But for Tan 618, the scale becomes absurd. Its event horizon would span over 2,600 astronomical units. That's 2,600 times the distance between the Earth and the Sun. Our entire solar system, out to its most distant planet Neptune, would fit inside it hundreds of times over. If you were to travel at the speed of light, it would take you weeks to cross from one side of this black hole's event horizon to the other. It is not merely a supermassive black hole, it belongs to a new, terrifying class, an ultramassive black hole. The birth of a giant. The existence of a monster like Tan 618, seen so early in the universe's history, poses a profound question for cosmology. How? How does a black hole get this big, this fast? The light we see from it is ancient, from a time when the universe was just 3.4 billion years old. This giant had to form and grow to its impossible size in a cosmic blink of an eye. This is one of the greatest puzzles in modern astronomy. The leading theory is a process called hierarchical merging. Supermassive black holes grow by swallowing gas and stars from their surroundings, but their most significant growth spurts come from merging with other black holes as their host galaxies collide. Over billions of years, a chain of these cataclysmic mergers could theoretically build a giant. However, for Tan 618, the timeline is uncomfortably short. Its immense size so early on would require a perfect, non-stop feeding frenzy on a scale that seems improbable, even for the chaotic conditions of the early universe. This has led to a more radical theory: direct collapse. This idea posits that in the primordial universe, certain gigantic clouds of pristine gas, thousands of light years across, could have become so dense and massive that they bypassed the usual process of forming stars. Instead of fragmenting into thousands of suns, the entire cloud collapses under its own gravity directly into a seed black hole. These seeds would already be tens of thousands or even hundreds of thousands of times the mass of our Sun. This would give a black hole like TON 618 a significant head start, making its rapid growth to 66 billion solar masses more plausible. It would have been born a giant and grew into a titan. The host galaxy of TON 618 remains a mystery. The quasar is so intensely bright that it completely drowns out the light from its own home galaxy. We are blinded by the very light that tells us it exists. This makes studying its environment and finding the crucial clues to its formation incredibly difficult. We are seeing the result of a crime, a galaxy being consumed by its own heart. But the evidence of how the culprit came to be remains shrouded in fire, the edge of knowledge. For decades, TON 618 has held the title of the Undisputed King. Its mass was determined using well-established, reliable spectroscopic methods. But in science, no crown is worn forever. The hunt for even bigger monsters is relentless, pushing our technology and our understanding to their limits. Recently, a new candidate has emerged from the Phoenix Galaxy cluster, a black hole nicknamed Phoenix A. Initial, more indirect estimates based on the energy it outputs suggest it could weigh a staggering 100 billion solar masses. However, its immense distance and the complex environment of the dense cluster it resides in make a precise, direct measurement extremely difficult. For now, it remains a tantalizing possibility, a challenger to the throne. But TON 618 remains the largest black hole whose mass has been confidently and directly measured through its accretion disk dynamics. The discovery of these ultramassive objects pushes the boundaries of theoretical physics. It forces us to ask fundamental questions. Is there an upper limit to how large a black hole can grow? Is there a physical mechanism, perhaps related to the accretion process itself, or the expansion of the universe, that caps their size? Some theories suggest a stupendously large black hole could not grow beyond about 100 trillion solar masses before the physics of its own accretion disk would prevent it from feeding efficiently. But these are just theoretical shorelines on an unexplored ocean. The universe is not obligated to conform to our expectations. From a forgotten dot on a photographic plate to the king of the cosmic abyss, the story of TON 618 is a testament to this truth. It is a profound reminder that for all we have learned, for all the wonders we have seen through our telescopes, we have only just begun to scratch the surface of what's out there. TON 618 challenges our models of galaxy formation and black hole evolution. It acts as an extreme benchmark, forcing us to refine our theories and to build new tools, like the James Webb Space Telescope, to peer deeper into that ancient darkness. What else lies waiting to be discovered in the vast, silent dark? Are there even bigger tyrants weighing a trillion suns, still reigning unseen in the deepest voids of space-time? We don't yet know, but one thing is certain. The search has only just begun. The host galaxy and its invisible realm. The story of TON 618 is dominated by the black hole itself, but this object did not form in a vacuum. Like all supermassive black holes, it resides at the heart of a galaxy. Yet, when we point our most powerful telescopes at the coordinates of TON 618, we see no swirling spiral arms, no elliptical haze of ancient stars. We see only the blinding point of the quasar. The host galaxy is completely invisible, utterly lost in the glare of its own monstrous core. This invisibility is not just a challenge for astronomers. It is a profound clue about the violent relationship between this black hole and its home. The energy pouring out from TON 618's accretion disk is almost beyond comprehension. It emits radiation across the entire electromagnetic spectrum, from radio waves to the highest energy gamma rays. This torrent of energy, often referred to as active galactic nucleus feedback, or AGN feedback, acts like a cosmic superweapon aimed at its own galaxy. It generates winds of hot gas and particles moving at a fraction of the speed of light. These winds can effectively blow the galaxy's own interstellar gas right out into intergalactic space. A galaxy's gas is its lifeblood. the raw material needed to form new stars. By stripping its host of this gas, TON 618 is effectively sterilizing it, halting all future star formation. It is not just feeding on its galaxy, it is actively preventing it from growing further. The galaxy becomes a red and dead system, populated only by old stars, its creative potential snuffed out by the very object at its center. This process is one of the most important regulatory mechanisms in the universe, explaining why the biggest galaxies aren't even bigger than they are. TON 618 represents this process taken to its most violent and spectacular extreme. But even if we can't see the galaxy, can we infer its properties? For decades, astronomers have observed a surprisingly tight correlation between the mass of a galaxy's central black hole and the properties of the galaxy's central bulge, specifically the average speed at which its stars are moving, known as stellar velocity dispersion. This is the M-sigma relation. It suggests a deep symbiotic evolution. As a galaxy's bulge grows, its black hole grows in near-perfect lockstep. It is as if the galaxy and its black hole grow up together, regulating one another's size. If we apply this established M-sigma relation to TON 618, we arrive at a startling prediction. For a black hole of 66 billion solar masses, its host galaxy's stellar bulge should have a mass of trillions of solar masses, making it one of the most massive galaxies in the universe. This would be a brightest cluster galaxy, or BCG, the dominant central galaxy found in the gravitational heart of a massive galaxy cluster. The problem is, building such a colossal galaxy in just 3.4 billion years is almost as difficult as building the black hole itself. It would require an unprecedented rate of galaxy mergers and gas accretion in the early universe. This creates a cosmic chicken and egg dilemma. Did a hypermassive galaxy form first, creating the conditions for its black hole to grow to an incredible size? Or did the black hole, perhaps through direct collapse, form as an oversized seed and then rapidly outgrow its host galaxy, breaking the M-sigma relation completely? In this second scenario, TON 618 would not be a partner in its galaxy's evolution, but a cosmic parasite, a freak of nature that grew far too large for its environment. The fact that its light outshines its host so completely may be the ultimate evidence for this imbalance. It is a king reigning over a kingdom that it has simultaneously built and rendered invisible and barren. The hope for resolving this mystery lies with new instruments. The James Webb Space Telescope, with its incredible sensitivity to infrared light, is uniquely suited for this task. Infrared light can penetrate some of the glare and dust surrounding the quasar, potentially allowing astronomers, for the first time, to detect the faint ancient starlight of the host galaxy itself. By measuring its size, its shape, and the motions of its stars, we could finally determine if TON 618 lives in the colossal galaxy predicted by theory, or if it is indeed an anomaly, a king without a suitably grand kingdom. Finding the galaxy is the next frontier in understanding this behemoth, a quest to find the faint ghost that haunts the edge of this incredible fire. The physics of an ultra-massive event horizon. The sheer mass of TON 618 is its defining characteristic, but it is the consequence of this mass on the fabric of space-time that is truly mind-bending. The event horizon, the point of no return, is not a physical surface, but a gravitational boundary. For TON 618, this boundary is an abyss of unfathomable size, so vast that it behaves in ways that defy our everyday intuition about black holes. Perhaps the most famous concept associated with falling into a black hole is spaghettification. This is the effect of tidal forces, the difference in the strength of gravity between your head and your feet. For a small, stellar mass black hole, the gravitational gradient at the event horizon is incredibly steep. An object approaching it would be stretched and squeezed into a thin stream of atoms, long before it ever reached the point of no return. Its end would be violent and instantaneous. For TON 618, the opposite is true. Because of its immense size, the curvature of space-time at its event horizon is surprisingly gentle. The difference in the pull of gravity between one end of a spaceship and the other would be negligible. An astronaut in a resilient ship could cross the event horizon of TON 618 without feeling a thing. There would be no violent forces, no dramatic alarms. One moment you are in the observable universe, able to send a signal home. The next moment you have crossed an invisible line, and you are sealed within the abyss forever. The crossing would be terrifyingly, unnervingly peaceful. From that moment on, your fate is sealed, not by a force pulling you, but by the warping of space-time itself. Inside the event horizon of a black hole, space and time exchange roles in a bizarre way. The direction towards the central singularity is no longer a place in space. It becomes a moment in the future. Just as we on Earth cannot avoid moving into tomorrow, an object inside the event horizon cannot avoid moving towards the singularity. All possible paths, all future timelines lead to the center. To try and move away from the singularity would be as futile as trying to stop the passage of time. The very fabric of reality is flowing into the singularity faster than the speed of light, carrying you with it. For an outside observer watching this journey, the view would be completely different, a direct consequence of Einstein's theory of general relativity. As the astronaut approached the event horizon, their image would seem to slow down. The signals they send back would become increasingly stretched to longer, redder wavelengths, their voice dropping to an impossibly low frequency. Their clock would appear to tick slower and slower relative to ours. They would appear to dim, to redden, and to freeze forever at the edge of the horizon, a ghostly after-image imprinted on the boundary of space-time for eternity. But for the astronaut, time would pass normally. They would see the entire future history of the external universe flash before their eyes in their final moments, as the light from a distant future falls into the black hole behind them. The journey from the calm event horizon to the central singularity would take hours, a final, inescapable descent. And what lies at the end? What is the singularity? Here, our science falls silent. General relativity, our best theory of gravity, predicts a point of infinite density and zero volume, a place where the laws of physics as we know them break down completely. This is almost certainly not the physical reality. It is a sign that we need a more complete theory, a theory of quantum gravity that can describe how gravity behaves at these infinitesimal scales. The singularity inside TON 618 is not just the end point for matter that falls in. It is the ultimate boundary of our current scientific knowledge, a place where the two great pillars of modern physics, relativity, and quantum mechanics must finally meet. It is a physical place in the cosmos that represents a purely theoretical frontier, rivals to the throne, the hunt for even larger monsters. TON 618 has held its title as the most massive black hole with a well-constrained measurement for years. But in the cosmos, records are made to be broken. The astronomical community is in a constant hunt for the extreme, and several other behemoths have been identified as potential challengers for the crown. These candidates highlight the diverse ways black holes can grow and the ingenious, though often indirect, methods astronomers use to weigh them. The most famous challenger is Phoenix AI, located at the heart of the Phoenix Cluster, a colossal gathering of galaxies some 5.7 billion light-years away. Phoenix AI is not a brilliant quasar like TON 618. It is a more quiescent, sleeping giant. Astronomers estimated its mass not by observing a glowing accretion disk, but by observing its effect on the vast clouds of superheated gas that fill the galaxy cluster. Powerful jets launched from the black hole's vicinity in the past have blasted out enormous cavities or bubbles in this intracluster medium. By measuring the energy required to create these bubbles, scientists can work backwards to estimate the power of the central engine. These calculations led to the staggering estimate of 100 billion solar masses. While this method is powerful, it is also indirect and carries more uncertainty than the spectroscopic measurement of TON 618. Phoenix A remains the leading contender for a more massive black hole, but its reign is, for now, based on circumstantial evidence. Another formidable rival lies in the galaxy Holmberg 15A, a supergiant elliptical galaxy at the center of the Abell 85 galaxy cluster. Unlike the turbulent heart of TON 618, the center of Holmberg 15A is strangely diffuse and faint. It has an enormous, low-density core, larger than any other observed. This is thought to be the result of a violent merger of two galaxies with their own central black holes. The two black holes would have orbited each other, ejecting stars from the center in a process called gravitational scouring before they finally merged. By tracking the orbits of the remaining stars in this depleted core, astronomers calculated the mass of the central object needed to hold them. The result was a mass of 40 billion solar masses. While smaller than TON 618, Holmberg 15A's black hole is significant because it's in our more local recent universe, and its existence reinforces the idea that such giants can be built through galactic mergers. It represents a different life stage, a quiet tyrant resting after its ancient wars. Perhaps the most exciting developments in the hunt for giants come from the very dawn of time. Revisiting the idea of direct collapse black holes, the James Webb Space Telescope is now peering into the cosmic dawn, observing galaxies that existed just a few 100 million years after the Big Bang. In this primordial era, JWST is discovering objects that are unexpectedly bright and massive. Some appear to be overmassive black holes in tiny, fledgling galaxies, black holes that make up a far larger percentage of their host galaxy AS mass than is seen today. These objects might be the oversized seeds predicted by direct collapse theories. While they are not yet larger than TON 618, their existence provides a crucial piece of the puzzle of how a monster like TON 618 could have formed so quickly. Finding these nascent giants is like finding the fossilized remains of an apex predator's infant form. The hunt for the universe's largest black hole is more than a cosmic contest. Each new candidate, whether it's a silent giant like Holmberg 15A or a primordial seed found by Webb, adds another chapter to our understanding of the cosmic ecosystem. The different methods of measurement, from accretion disk spectra to X-ray cavities to stellar dynamics, each provide a different window into the lives of these giants. While TON 618 remains the confirmed king, the rivals are circling. The quest pushes our technology and our theories to their absolute limits, reminding us that there are likely even bigger monsters hiding in the dark, waiting to be found. The end of an era. The future of TON 618. The blazing spectacle of the TON 618 quasar is a portrait of a black hole in its prime, active, growing, and ferociously powerful. But this phase, for all its cosmic grandeur, is fleeting. Like a fire that consumes its fuel too quickly, the quasar era for any black hole must eventually come to an end. TON 618's reign of light is temporary, and its long-term future will be one of profound silence and almost eternal darkness. The quasar is fueled by a massive and continuous inflow of gas and stars. This level of feeding can only be sustained for a few tens of millions of years, a mere blip in the lifespan of a galaxy. Eventually, the black hole will have consumed most of the easily accessible material in its vicinity, or its own powerful feedback will have blown the remaining gas away. As the fuel supply dwindles, the accretion disk will begin to thin out. The cataclysmic glow that outshines a 140 trillion suns will flicker and fade. Over millions of years, TON 618 will transition from a hyperluminous quasar to a more common active galactic nucleus, and then, as the last vestiges of its meal are swallowed, it will become dormant. The monster will not disappear. The 66 billion solar mass black hole will remain, a silent, invisible tyrant at the galaxy's core. Its gravitational influence will still orchestrate the dance of stars for billions of light years around it, but its luminous roar will have been extinguished. It will become a sleeping giant, much like the black holes we see in the center of our own Milky Way or the nearby Andromeda galaxy, vast, powerful, but dark. It would only reawaken if another galaxy were to collide with its host, providing a fresh supply of gas to reignite the quasar for another brief, brilliant era. But what is its ultimate fate? In the far, far future of the universe, even these silent giants must face their end. In 1974, Stephen Hawking made a revolutionary discovery that united general relativity with quantum mechanics. He theorized that, due to quantum fluctuations at the edge of the event horizon, black holes are not entirely black. They should emit a faint trickle of thermal radiation, known today as Hawking radiation. This process causes a black hole to lose mass ever so slowly. It effectively evaporates. For a stellar mass black hole, this process is incredibly slow. For a supermassive black hole, it is almost incomprehensibly slow. The rate of evaporation is inversely proportional to the black hole's mass. The bigger it is, the colder it is, and the slower it evaporates. For TON 618, the timescale for its complete evaporation through Hawking radiation is a number so large it borders on the nonsensical. It would take an estimated 10 to the power of 100 years, a Google years, for TON 618 to fully radiate away. This is a timescale that dwarfs the current age of the universe by a factor of trillions upon trillions of trillions. Long after the last star in the universe has burned out and cooled, long after galaxies have dissolved and protons themselves may have decayed, in the cold, dark, heat-death era of the cosmos, the universe's ultramassive black holes will be the last remaining large-scale structures. They will be the ultimate gravestones of a once vibrant cosmos, and one by one, over a time scale that defies human imagination, they too will dissolve. The evaporation of TON 618 will be one of the final significant events in the history of our universe. Its immense mass energy, accumulated over billions of years, will be slowly and silently returned to the void as a faint whisper of heat, leaving behind nothing but empty, flat space-time. Its story begins in the brilliant fire of the cosmic dawn and ends in the absolute zero of the ultimate cosmic night. The cosmic mirror. What these monsters teach us. From a forgotten dot on a photographic plate to a titan weighing 66 billion suns, the journey to understand TON 618 is a story about the scale of the universe. It's a journey that forces us to confront numbers that feel impossible and concepts that stretch the limits of our imagination. But beyond the shock and awe, what do these monsters truly teach us? What is the human meaning of a leviathan that exists 10 billion light-years away? The answer is that TON 618 and objects like it act as a cosmic mirror, reflecting not only the nature of the universe, but also the nature of our own quest for knowledge. Firstly, these objects are the ultimate affirmation of our understanding of physics. The very same laws of gravity that govern the fall of an apple on Earth and hold our planets in orbit around the Sun, when scaled up to an unimaginable degree, create TON 618. There isn't one set of laws for here and another for there. The principles of relativity are woven into the fabric of the cosmos everywhere. Seeing them operate at such an extreme confirms the power of our scientific theories and gives us the confidence to probe even deeper mysteries. Secondly, TON 618 provides us with a profound sense of perspective. In the face of its scale, our human concerns, our history, our planet, even our entire solar system are rendered utterly insignificant. Its event horizon could swallow our civilization without even registering the meal. This perspective can be terrifying, but it can also be liberating. It reminds us that we are part of something indescribably vast and ancient. It tempers our hubris and encourages a sense of humility and wonder. It connects us to the grand cosmic narrative, a story that began long before us and will continue long after we are gone. Furthermore, TON 618 helps us reframe our view of black holes. For a long time, they were seen purely as agents of destruction, cosmic vacuum cleaners that consumed everything. But we now understand them as integral parts of the cosmic ecosystem. They are not just destroyers, they are creators and regulators. The energy they release in their quasar phase, like the energy from TON 618, sculpts galaxies, dictates where and when stars can form, and enriches intergalactic space with heavy elements. They are the violent, beating hearts that drive galactic evolution. Without them, the universe and galaxies like our own Milky Way would look very different. Finally, and perhaps most importantly, ultramassive black holes like TON 618 are signposts pointing toward our own ignorance. The singularity at their heart represents a place where our most successful theories fail. The information loss paradox, the question of what happens to the information of the matter that falls into a black hole, remains one of the deepest unsolved problems in physics. These objects are not just curiosities, they are natural laboratories for testing the absolute limits of science. They force us to ask the biggest questions. What is the nature of time? What is space made of? And how did it all begin? The quest to understand TON 618 is therefore a reflection of the human spirit. It is a testament to our relentless drive to explore, to measure, to understand, and to find our place within the whole. We look out into the abyss, not just with fear, but with an insatiable curiosity. For in the heart of that distant, impossible fire, we find not just the secrets of the universe, but also a deeper understanding of ourselves and our unending desire to know. The cosmos is filled with monsters, but by studying them, we become less afraid of the dark.